Okay, so today we are going to talk about the visualization of the non-adiabatic coupling. Last week we talked about how to generate the coupling files from the molecular dynamic calculations, and in this session we want to generate the visualization and actually Redfield tensor out of the calculation. So just to remember a brief summary first. So you can hear me, right? Okay. Okay. To do the coupling calculation, first we need to do the geometry optimization at the first step, ground state calculation. Then we need to copy the count car in the postcard file and anneal the system, do the heating calculation. Similarly, using the count car of the heating as a new postcard file for molecular dynamic calculation. And as we reviewed last week, after finishing the molecular dynamic simulation for instance, around 1000 time step and considering atomic motion, we will do the coupling calculation to generate the coupling files. And today, the last step, we want to plot, actually visualize the coupling data file that we generated last time. So what do we need to do the visualization actually of the Redfield tensor? First, the energy pop that we generated last time. For instance, this is a snapshot of the system that I'm going to visualize the...
May I interrupt in the middle?
Sure.
So, as it is declared by words, it sounds like the goal is to visualize Redfield tensor. Visualization is cool, but the primary goal is to compute Redfield tensor, which is a procedure that averages couplings. So, because Redfield tensor will be a prerequisite for the next step of quantum dynamics.
Exactly, yeah.
Yep.
And so, also visualization. So, yeah, thank you for clarifying. As you can see here, we consider the 20 actually orbital near the band gap, 10 unoccupied orbital and 10 occupied orbital, and totally 20 orbital to do the coupling calculation. So last week we generated the coupling files in the format of coupling, for instance, 001 to coupling 999, totally 1000 coupling files. Coupling files for 1000 time step that we did the calculation. And for my calculation, the coupling file was generated in the zipped format. So if somebody need to unzip that files on the actually on it, HPC can use these commands to unzip those files to a MATLAB readable format, actually, to the text. So next step is to download the coupling files from the HPC to your local computer. For instance, here I did the calculation for a PCBM Florian system. I just have 400 coupling files, so it's a little small to see, but I make a directory, put the MATLAB file, energy pop file, and the coupling files in the same directory to do the calculations. Next step, Dr. King, let me stop share, and because if it's not in the screen mode, you may not be able to see that. Share to screen, slideshow. I hope this time you are seeing the right screen. Okay, very good. So this is the script that I briefly modified that, add the name of Revised Summer 2021 at the end of the screen. So this script, we just load the energy pop. So, and we just need to specify the number of time step that we want to calculate the Redfield tensor as an average, and so for sure number of the coupling files. Here, for instance, I did the calculation for 1,000 time step, but I just choose 400, and also I just have 400 coupling files so far, so I didn't finish the simulation.
Here,
Yeah.
So I noticed that Amir and several other attendees did modify this correlation script in a good way. So maybe we can agree to save them on the Photon and on NERSC in the bin directory or bin/MATLAB, so that each of the group members can try other version and see if it is more comfortable to. So instead of sending it by email, just save it there.
Okay, you will save it, or
No,
I should?
the author better save it.
Okay, sure. I will save that in the bin directory. Sure.
Yeah, thank
you. Yeah, thank you, Dr. Kulin. So for starting running the MATLAB code, you just need to specify the number of desired time step. I choose 400. We will see why just 400 is enough, and also number of coupling files usually should be around 1,000 if you calculate all coupling files for the simulation, but so far I just obtained 400 coupling files. Then I set this as 400. So there are some other parameters need to be specified. I just a little organize them. Omin means the first number in the first orbital number in energy pop file. For instance, here 147 orbital marks the latest number in the orbital file, here 166, and number of orbitals, which is 20 here, and I just add a small loop to find the HOMO from the energy pop, where the occupation is below 0.5, just to specify the HOMO number here, which is 126. And yeah, just you need to specify these two numbers and just run the MATLAB code, as you can see here, because the coupling files for 1 to 9, 10 to 99, and 100 to 1000 has a different naming. So we need a different prefix here to specify those names, which are developed before by Dr. Kane and his colleagues. So yeah, again, just if you want to use this script to visualize your data, you just need to specify these two numbers. So the code for the rest of it should be fine to visualize your numbers. So if you run this MATLAB codes on your local computers, if you want to run again, you need to have energy pop, the MATLAB script, and coupling files, all of them in the same directory, and then try to run the MATLAB code. And this is the visualization of the transition probabilities. Actually, this code calculate, for instance, here we have 20 orbitals. This code generate and save a matrix, a 20 by 20 matrix, because we have 20 orbital. So the matrix name is RRR, which is Redfield tensor as an average over the different time step. And this plot is a visualization of that matrix. So as you can see, it should be always a maximal transition probability near the diagonal of the matrix. And I also have a question from Dr. King about that. As you can see here, I specify LUMO and HOMO. You can see that for the LUMO and HOMO, at this point, we have a very small transition probability. And yeah, these are the results that we can find from here. Dr. Kinin, I see you on mute. So do you want to add something?
No. If you have question, I can comment. If you don't, keep going. The probability of transition from the state to itself, from the orbital to itself, doesn't make sense. It should be either 0 or infinity, or we should exclude it from consideration.
So what from HOMO to LUMO?
From HOMO to LUMO, you need to look on just one little square away from this. So not on the main diagonal, but the off-diagonal element. Like your two lines intersect at
HOMO and LUMO.
10, in
10, 11 actually.
Okay. Yep, and it is typically, it is right way. The intersection of these lines is a transition, non-radiative transition from LUMO to HOMO, and it is typically very small. Aaron, would you like to comment on LUMO to HOMO transition and what it corresponds to in real life and why it is so small?
I guess that would be the non-radiative recombination. So it's the combination of the electron and hole, which is usually much slower than like a LUMO +4 to LUMO +3 transition. If that makes sense.
It makes sense to me. So it is lifetime of the excitation, and for molecules, it typically has values of inverse nanosecond. So the rate, like the recombination, happens in of the order of magnitude of nanosecond, 10 to the -9 of the second, and relaxation typically happens on the order of magnitude of picosecond, so 10 to the -12 of a second. So this LUMO to HOMO is expected to be 1,000 times lower than the nearby sticks.
Okay. Okay, thank you very much, Dr. Klin. And so the next plot is the autocorrelation factor. As you can see, usually as the time goes up, we expect the autocorrelation function decay from 1 to near the 0. You can see that, for instance, at maybe 360, it reached it to the 0 value, and after that it has a small fluctuation around the 0 value. So for this system, maybe if we change the system, or for instance, or to larger system, or to my main system, which is a blend of conjugated polymer and PCBM, we need longer time span to reach those to decay to the 0. So yeah, these are two plots that I had to show for today. Any question?
Okay, please join me thanking Amir.
Thank you. So before asking question, I have a question, Dr. Klin.
Please.
Regarding to the Aaron comment, this is my confusion. So we always expected over the excitation, it would be much easier or more probable to, for instance, have electrons promoted from HOMO to LUMO, because maybe the much lower energy, transition energy, is needed for those kind of excitation. So here, I do not have enough study on this transition probability, but before plotting this, to be honest, I expected to have a larger value on HOMO to LUMO tile here. Mm-hmm. But I was surprised. So could you please a little more clarify me?
With great pleasure. And if anyone in the audience wants to give comment right away, please do. David, would you like to comment on your vision why LUMO to HOMO is very non-intense?
the way I think about it is that pretty much how Aaron described it, that we're looking at the non-radiative decay, which for HOMO to LUMO is very slow in comparison to interband non-radiative decay. So that, I mean, there is a peak there. It's just so small that you can see it.
Mm-hmm. Yeah, always correct. Yeah, thank you, David. Amir, let me add. So I imagine myself hearing all these things for the first time, and some terminology can go not absorbed. So the keyword is non-radiative.
Mm-hmm.
In everything you did before, you are thinking about oscillator strength and absorption. When
Yes.
optical transition from HOMO to LUMO is quite intense in most systems. So optical means radiative, especially if it goes back from LUMO to HOMO, the energy radiatively recombines back to ground state. And the key word in what Aaron and David were telling is non-radiative. It means the energy disappears from system without emitting a photon, without emitting light. It means it should dissipate into heat. And your intuitive expectation was related to radiative channel interacting with electromagnetic radiation, where all vacuum around us is full of normal modes of electromagnetic radiation at any available frequency. So basically anything will radiate sooner or later. If we speak about non-radiative, it means that this amount of electronic energy between LUMO and HOMO should go into heat, into oscillations of some ions in the model. But if there are no ions that oscillate with such big frequency, then no one can absorb this energy, and it will stay there for a long time. If your model would have low gap of the order of like 0.1 electron volt, then there will be a lot of normal modes that would happily absorb electronic energy. And because due to this reason, it's very hard to create infrared emitter. But if it is like in the optical range, the lifetime of LUMO to HOMO, it doesn't recombine through heat. It prefers to go through optics. But in these images, Redfield, it tells us only the non-radiative, how the energy is released via heat. Does it answer your question?
Yes, yeah. I found my mistake. Thank you.
Any questions to Amir? Questions 1, questions 2, questions 3. I think no one wants to ask questions. There were some questions on the way, and special thanks for modifying the code, and we look forward to find this version in the binary directory and try it. Yeah, please join me thanking Amir once again.